Welcome to this final afternoon of the symposium on Professor A.K. Raychaudhuri. We have two talks this afternoon by leading experts on GR. The first talk will be by Professor Pankaj Joshi. Professor Joshi was a professor at the Tata Institute of Physics. He has worked on various aspects of gravitation, in particular on what are the nature of the eventual singularities if they go on to form. And currently, he's at Ahmedabad University. In fact, he will be telling us today about Professor AKR and spacetime singularities. Over to you.
In the first place, my warmest thanks to the organizers for planning this excellent meeting in the memory of none other than Professor Amal Kumar Raychaudhuri. When we speak of Professor Raychaudhuri, I would say that, needless to say, he has been a most inspiring figure in the Indian cosmological context. Not only that, at the world level, his contributions are known today. My associations with Professor Raychaudhuri have been deep and intense. I'll explain very briefly before going to the main topic of my talk. When I was, I think, MSc or PhD student, probably in 1977, way back, we organized an IAGRG, you see, in Bhavnagar. And Professor P.C. Vaidya and you see, some other relativity veterans were the people who established this society, and Professor Raychaudhuri came. Of course, Professor Vaidya also was there. And then subsequently, I kept meeting Professor Raychaudhuri, and in fact also Mrs. Raychaudhuri, because they traveled to many meetings together. I, being an inquisitive, you see, young person at that time, would always take opportunities to converse with him, and he would very gladly oblige. I today will clarify, in fact, Professor, in the morning, Sengupta, clarified or pointed out when the development happened of singularity theorems, what was the reaction of Professor Raychaudhuri, what were his what should I say, reactions and comments and suggestions and so on. So I'll clarify to you the actual role of Raychaudhuri's equation in the development of space-time singularities, which eventually led recently, I think, to 2020, to the Nobel Prize to Professor Roger Penrose. But before that, what I recall vividly is once at the inauguration of, I think, Bose Institute, maybe it was 1975 or something, when I was a student. I went to Calcutta, and E.M. Lipschitz had come. Landau Lipschitz fame, Lipschitz had come. And Lipschitz claimed that it was Landau who had given this equation describing the convergence of matter in space-times. And it was wonderful for me to to watch at that time that each of them, you see, ran into an argument. And Lipschitz would tell something, and Raychaudhuri will, stand up and go to the blackboard, and, he will write something, he will argue something. Lipschitz would again come. So it went on, I think, for some time, actually. It was a very deeply impactful debate. There are numerous things, actually, that I could tell, the stories, so to say. But there was a discussion on courage, a pointer that you mentioned in the morning. So I used to brief him about our work, to him and Professor Vaidya, all the time. So when we wrote, you see, some first papers on gravitational collapse, I was also doing cosmology, by the way, earlier. Neutrino masses and, you see, their upper limits from cosmology. But then somehow, you see, this field grabbed me, to put it that way. One problem after the other just came up. And, it sort of led to one work to another. But when I discussed with Raychaudhuri, I have, you see, his detailed letter or letters written to me. It would be too much to display, which I won't do here. But he said that, I asked him that, look, these are the results which are coming out. Gravitational collapse. As far as the formation of event horizons is concerned, such very interesting features are observed. I'll clarify that in a moment when I go to my talk. And what do you say, sir? Because these are, sort of interesting behavior. Of course, we have published in best of the places, but still, we want to know. So he said, just carry on. Why worry? You just follow the logical path of science. So that showed, you see, his spirit. And he would always, you see, smilingly encourage, you see, the generations of the people. So he and Vaidya have been, so to say, the father figures for Indian relativity. And it is that heritage, I would say, which has kept us going for really quite some time. I'll come back to these things maybe in a moment. But just to build up Raychaudhuri and cosmology. So this is the, universe of galaxies. As you know, each of these galaxies contain some 300 to 400 billions of stars. But the very important point is, there are stars which are very large compared to sun. You see in a corner there, you can see the sun here. This is working fantastic. So, thank you. So you see, compared to sun, there are big stars in our own galaxy, elsewhere, and so on. And then, of course, we have most interestingly and most importantly, major new observational missions and facilities coming up, which are like, you see the Square Kilometre Array, the TMT, 30-meter telescope, LIGO, LISA, Event Horizon Telescope, and such others. And as we were discussing again in the morning, it's too hard to push on Earth the energy scales. Too expensive and too difficult. Whereas out there, there might be very powerful energy sources, and all we have to do is observe, note down the, you see, the findings. The important, very important point is we are probing ultra-strong gravity regions in the cosmos already, so to say. Now, here, You see, I would like to go closer to the contribution of Raychaudhuri. I would like to scientifically clarify what his actual contribution was in the, you see, singularity theorems. As we had discussed, probably in the earlier talks, the Penrose and Hawking theorems basically show that space-time singularities form in gravitational collapse and in cosmology. Okay, and what are these singularities? There was a huge debate by Robert Garrosh and Stephen Hawking and Roger Penrose and others. So, what we know is that general relativity implies that under reasonable physical conditions, a collapsing massive star must terminate into a space-time singularity. You see, where the densities, curvatures, and all physical quantities diverge, basically. But what we do not know as far as the gravitational collapse is concerned, this is the theorem of Penrose. That is the occurrence of space-time singularities in the form of geodesic incompleteness. What we do not know is whether, let us leave the cosmology apart for the moment. If we talk of gravitational collapse, what we do not know is whether these singularities are, whenever they form, you see the event horizons, whether they will always come and they will always, you see, cover the singularities. So the basic question at the very foundation of entire of black hole physics, and I will emphasize that this is at the foundation of very, existence of black hole physics, is that are singularities of collapse visible to faraway observers in the universe? And you see what is called cosmic censorship. So that protects us from visible singularities. But it is a hypothesis. It is a hypothesis, and you see, people thought that one fine morning Roger Penrose will, give us the proof. And Penrose did give us the singularity theorems, showing the existence of singularities in the form of geodesic incompleteness. But the theorem for the existence of event horizons covering the singularities whenever they occur, so that turned out to be a very, very long search. And as of today, the question has not been resolved fully to the satisfaction of, you see, the community. And the community is well aware. And this question is so important. Why? Because it is at the foundation of very thermodynamics of black holes. When you show the area theorem, when you show the first law, second law, and all that, you assume that the space-time is technically what is called asymptotically predictable and flat. See, if you read Hawking and Ellis, by the way, that is another story of my, you see, connection with Professor Raychaudhuri. I visited, you see, TIFR, I think sometime in 75, 76 or something. And there was a mention that Professor Raychaudhuri said that these techniques that Hawking and Penrose developed, what are they? I mean, and there, you see, I ordered a book which was just published at that time, The Large Scale Structure of Space-Time. I still remember going to Blackie and Sons opposite to the VT station, and perhaps I might be the first person to order that book. Hawking and Ellis paying a lot of money. We didn't have, big grants, and you see, I paid my sort of, but I, you see, then read that book. And you see, the thing is that I was in a bad or good habit of, I had a red ball pen. So, you see, whatever I thought interesting, important, I'll underline. Write some remark. That might be, not so intelligent remark. But whatever came to my mind, I wrote in the, margins, those remarks and so on. So, in next meeting, when I met Professor Raychaudhuri, I'll of course carry that book with me because I was reading, and then I will refer to it. And then, you see, these developments were taking place. So, Raychaudhuri, said, oh, you got this Hawking and Ellis? I said, yes, show me. And then, when he flipped through it, he saw, lots of red lines. So he was very impressed. Oh, you have read this book? I said, I have read, but I didn't say how much I understood or how much I didn't, not that I understood everything. Obviously, it is considered to be a very tough, book. But I had, tenaciously gone through and read most of the. So then he was very happy, and that again, sort of intensified our bond discussions because he asked many questions related to that. But the point is now, here comes, you see, what I wanted to clarify regarding. You see the Raychaudhuri equation. Yes, I got. So there are two things. One is, you see, focusing of matter in a space-time. And the second thing is space-time manifold. I'm not sure whether this word was used in earlier, talks, but this was a big deal. Manifold, you see, space-time manifold. It's a differentiable manifold. The space-time is a space-time. It is four-dimensional. We heard about dimensions and all that, but this is where AKR came in. So he gave this equation, as you all know, is equal to some minus some 2 sigma square and theta term and then omega term. So this was the Raychaudhuri equation, which described basically how the matter that is evolving in the universe or in gravitational collapse, how that is affected. This is the most important term. Those who do not know the general relativity, I'll clarify for them that this is basically the matter part. This RAB contains the matter and what focusing it, and this theta is so-called expansion parameter. That is how the matter, you see all these galaxies are evolving in time. So how either they go away from each other or in collapse, how the particles come together. So that is one thing. And the other thing is this causal structure of space-time manifold. So this is focusing in space-time. Now the great thing about the Raychaudhuri contribution is that, I think this paper was written in 1955, right? Published in 55, okay. Okay, so you see in that duration, the great thing about the whole thing was that after the Einstein equations, most of the work that was done was solve this very complicated equations. Solve. How to solve them? Nobody knows how to solve. So what do? You have to write a paper. Mathematics departments in India, in, you see, North, in various places. So you impose simplifying conditions. Spherical symmetry is nothing. I mean, they will impose many, many more things, which I will not go into details. But the point is, kuch solution nikalo. And these are very complicated equations. You see, second order, non-linear, partial differential equations. So, theek hai. I mean, research. Ho raha hai. But, and then you see the top people in the world where, you know, their attention was mainly on quantum theory and so on. I mean, 40s and 50s and major developments. But then it was this particular equation that regarded in a general way, without any artificial assumptions, the gravitational focusing in a space-time. No assumptions whatsoever, I emphasize, and that is the most important point. And that is why it became useful for the singularity theorems. When I talk of singularities, again, it's a very major history. Sorry, but I must tell you a little bit of that. You see, people said, oh, this Schwarzschild singularity, R equal to 2m. So people argued that it is some artificial thing and, you know, the general relativity breaks down, this and that. But then it was, again, the global approach which told you that really it is a coordinate singularity only, nothing is really diverging there, no physical quantities. Then came in the Kruskal extension. So that was the beginning of global structured thinking, which was at the foundation of that causal structure business. And now, it was widely believed, Lipschitz and school, you know, argued that really speaking, all singularities will go away. When you consider more general space-time, Schwarzschild, FRW are very special models and not so important. Of course, today I have to be very careful if I say FRW is special. But it is, you see, a special model. But the point is, Raychaudhuri, when he wrote his equation, it was completely free of any such assumptions under which, for example, the Friedman was obtained and, you know, many other solutions were obtained. So the point is that ultimately, you see, it was the singularity theorems which settled the issue. Now, how it settled? Raychaudhuri equation, what it told was that if you have a congruence of matter evolving in time, okay, then this equation forces the trajectories to cross sometime in future. It is called focal points or conjugate points. So this showed, implied, conjugate points in the trajectories of matter. Now this causal structure is a complicated subject, but to cut the long story short, what this showed was that for certain null hypersurfaces and so on, when you consider this type of congruences, then conjugate points must not occur. Raychaudhuri equation said very clearly conjugate points must occur under this and this situations, and this causal structure analysis showed when on certain null hypersurfaces and so on, the conjugate points must not occur. So then, if you have matter in the space-time, satisfying certain energy conditions, what are called energy conditions. Then what happened was, in order for conjugate points not to happen, the geodesics simply must not proceed beyond a conjugate point. And that geodesic is, an incomplete non-space-like geodesic. So it was in that sense that this entire area was put together with the Raychaudhuri equation, when the conjugate points must occur and when they cannot occur. So then matter was there, focusing was going on all the time, conjugate points have to occur. So then you see the geodesics, because in order to avoid the conjugate points, the trajectories must be incomplete. So in summary, this is the singularity theorem. I think I have not compromised too much in saying it this way, because singularity theorems are supposed to be very complicated. But roughly, I have told you in a correct way what their essence is. So if this equation were not there, then this would be a wonderful, beautiful analysis using the differential geometry and so on. But this equation turned out to be crucial. So with Raychaudhuri, I have had a lot of discussion on this, this part. In fact, later in his life, he wrote, a few papers, if you recall. Some of you who might have, some paper was written by Sinovilla and so on. And then you see in that connection. So we again had a lot of discussions. All in all, I mean, my God, he was in extra dimension. As was mentioned, So large extra dimension, or, so, it's a state of mind, I mean, you see, what things we think of throughout our lives. We had, Narayan, he is here. We organized, you see, a conference at Jadavpur University, workshop. And these people were there, I think, doing a lot of work, Asit Banerjee, Sriranjan Banerjee, and so on. We had invited Professor Roger Penrose. Raychaudhuri was at that time very regularly visiting. So anyway, there are many, many memories. The important point is, you see, this state of mind, they stayed in, that he worked in a college. And, what facilities he had in those days. And today we have so many facilities. Professor Vaidya, so many, difficulties. I know that personally. These two movies you must see, Raychaudhuri, and there is another movie on Vaidya also. Stars will collapse. Large stars will fail to form a neutron star. There will be a continual collapse. There will be no balance, you see, achieved. Sun, if it, runs out its nuclear fuel, it will become, I say, white dwarf, supported by electron degeneracy pressure. The neutron star will be supported by neutron quantum forces, if I speak a little loosely. Then, if for very large mass star, that will not happen. All these forces cannot balance. And then, you see, we have the regime of black holes. So this is one of the most important key issues in astrophysics and cosmology. As I was telling, that what happens when a massive star, you see, dies. Continual collapse, well, you need Einstein's theory of relativity, and the standard paradigm is a black hole will form, but that would have a singularity at the center, and then there will be an event horizon. There will be a photon sphere. I'll come to that when I talk of black hole shadows in a moment. They are supposed to be, this very high energy objects are supposed to be, very useful in explaining this ultra energy generation in the galactic nuclei, the jets, and so on and so forth. So the standard paradigm is, you see, an average star will end up as a white dwarf, but if there is a massive star, either it will be a neutron star if the mass is not too high, or it will be a black hole. But then, as I said, the key problem still remained. You see, do all massive stars collapse to a black hole only? Now, you see, the model was this, Oppenheimer and Schneider. Oppenheimer was in a lot of discussion recently, this movie and so on. I think there are 2 lines in that movie on, you see, his solution of black hole. So this is the Oppenheimer-Schneider model. You think of the time as, you see, vertical thing. This is a star which evolves in time and, you know, forms a space-time singularity. The point is, a lot of assumptions in the Oppenheimer-Schneider model, and very justifiably, because it's very difficult to solve these equations, and that too for a dynamical scenario. So the entire star collapses, a space-time singularity forms, but the beautiful thing is that before the singularity forms, the event horizon forms way earlier, and it completely covers the space-time singularity. Now, cosmic censorship hypothesis might have been mentioned, but I'm not sure whether any specific statement, mathematically or physically rigorous. So the point is that whenever generically the star will collapse, the same thing will happen. For example, stars would be inhomogeneous, typically higher density at the center. They may be rotating, they may not be completely spherical, so on and so forth. So the general statement is that in gravitational collapse, and this is very important, in gravitational collapse, it is a statement about gravitational collapse. It's not some general vague statement, cosmic censorship, that whenever singularities form, they will be always covered. Now, a simplest modification, because you see at the time of Oppenheimer and Schneider, it was very difficult to solve Einstein equations and work out everything. But subsequently, Eardley and Smart did some small numerical, simulation of the collapse. Not very clear. Christodoulou, then 84, did a very special example. Now, that singularity was shown to be somewhat weak and not so important. But then when we wrote our paper, especially in 1993 and a bit earlier, if you do the following, that rather than completely homogeneous density, let the density be somewhat higher at the center. No phantoms, no ghosts, you see, I'm not doing anything funny. I'm only asking the density to be somewhat higher at the center. So the profile is higher density and falling away. The immediately most interesting thing is from the causal structure results, you find out. So we use these things, quite heavily. So slowly, after many years, I understood Hawking and Hill is little better compared to those days when I used to, just mainly underline. So using those things, we examined the structure of event horizon and apparent horizon. I can give you the mathematics is simple and beautiful. Maybe some other time we will discuss in more detail working out the things on the blackboard. But the point is event horizon no longer forms way earlier, but it forms, just at the time of singularity, and as it turns out that there is a family of trajectories escaping. All these things can be explicitly worked out. And the important point is all I have done is make the density inhomogeneous higher at the center. So I have not done anything funny. This whole thing was debated, my God, like anything in those years. And there were lots of emotional upheavals, because this is something different, because people would find it strange that you do something so simple and the causal structure changes. But then lots of people have repeated these calculations by now, and it turns out that it's not wrong. Okay, it is okay within the. So you see, the point I am trying to emphasize is general relativity is a very subtle theory. The causality, is playing a very major role. Event horizons, apparent horizons, their behavior. So causal structure is very, very important. These are, some equations of, gravitational collapse. Then we did in a much more generality these calculations. And by now, many other groups, you see, if you, just give on this inspire, this search, then now you see that there are, many, many more papers. The key point that emerges is that if you have a regular initial data, defined at a constant slice of time, and if you evolve it in future, then depending on the initial data that you choose, for example, completely homogeneous data versus a slightly inhomogeneous data, but now you bring in pressures also, then depending on the initial data, you can have, subject to energy conditions, either the horizons covering or not covering the singularities. So what does this mean? For particular models, you see, this is the visible singularity region, and this is the black hole region. I would rather like to call them visible singularities, you see, because this terminology like cosmic censorship and naked singularities, and I mean that people in the beginning it's scared, but now I argued, you see, with some of my co-authors, I said I would throw out the paper, I would like to say singularities visible or otherwise, and they fought with me. They said, what's your problem? I mean, we call them, what is there in the literature. So anyway, the point is non-zero major. So the paradigm that is emerging or has emerged is massive stars, become black hole or exploding fireballs. I'll justify this term in a moment. A big deal, New York Times first page article when Stephen Hawking accepted. I was invited to write an article by the well-known scientific American magazine. It became their international cover story. The key point is, astronomers, you see, asked me when I talked with them, we don't care, for your theory. Whatever, is the outcome of collapse and whatever equations you work out, it's okay. Tell us if, such singularities are visible. See, this is very important because near the singularity, there was a mention in the morning of quantum gravity. So if such singularities are visible near the singularities, the densities, the pressures, all the physical quantities are very, very high. So if they are visible, then, you can have possible observations of this ultra high density regions. So this, in a paper with Daniel Malafarina and Ramesh Narayan, we worked out the accretion disks around black holes and singularities, naked singularities. And the most interesting feature that happened was that this is the Schwarzschild black hole, where the emission from the accretion disk, decays after a certain cutoff. However, in certain in the models that we considered, there's a long tail in very high frequency. So this is a distinctly sort of observable feature. A lot of discussion on this. Now, there are, you see, a lot of other developments on observational side, but for the lack of time, I'll not go into that because I want to devote a little time on black hole and singularity shadows. But the point is, as I just mentioned, if the naked singularities, which are hypothetical astrophysical objects, did form in collapse, can we then observe and see the quantum gravity effects taking place in their vicinity? So this is one of the questions, in fact, Robert Wald asked in one of his papers, that it would be exciting. the radiations coming from the very core. In one of our papers published in Physical Review Letters, we used the loop quantum gravity mechanism. It was called quantum evaporation of a naked singularity. We find that in the very final stages of the cloud, this R is the radius of the cloud. So when the radius of the cloud is very, very small, there is an explosive, evaporation due to the loop quantum gravity effects. The pressure turns out to be, minus 9 times the rho. So very heavy negative pressures causing this kind of effects. Let me come to the black hole shadows in my sort of final sort of part. As you all are aware, because this is very interesting and very topical, as you are aware, we have been searching the nature of the galactic center actually. So what is it there, and can we actually detect an event horizon, which would be a very definitive proof for the so to say the formation of horizons and so on. So the telescopes spread on various radio telescopes spread on various parts of the earth and constituting a major telescope, radio telescope, and then shadows are supposed to be observed. So we observed earlier this M87, and recently, in the last year, month of May, this SGR A star, our own galaxy shadow. I should have mentioned that, we examined many properties of, this objects. One very interesting result, this thing was mentioned. Here is an object, and then, this perihelion kind of a thing. In a space-time, if it were a naked singularity, then, one of our students, Parth, showed that, it will be a negative precision as opposed to the usual positive precision. So several intriguing theoretical discussions have been carried out with, Parth Babania, Dipanjan Day, who was at IIT Kanpur, and then, of course, Daniel Malafarina and others. I have not made a list, but you can see the collaborators in the Inspire. The point is that when you talk of the black hole shadows, the exercise that we carried out, in collaboration with, Prashant Kosherlakota and Rajibul Sheikh and Ramesh Narayan, of course, was that the Schwarzschild black hole will create a shadow. Theoretically, here you do the observation. But if you take a Schwarzschild black hole or a Kerr black hole, that will create a shadow. So what turned out was that even if you had, a naked singularity, that is a singularity without horizon, then that also give very similar shadows, just as the Schwarzschild black hole would give. So this caused, I think, a lot of intriguing discussions and debates. And in the recent Event Horizon collaboration series of papers, when they tried to explain this SGR A star shadows, there were some issues regarding some angles and polarization and so on. So then they took, the alternative models, and they described our models as best black hole mimickers, and they cited these papers. I cannot go into the detail right now. But again, the second thing is collision of black holes and the gravitational sort of production of gravitational waves and so on. If you see my book, The Story of Collapsing Stars, because after the Scientific American article, there were huge discussions. So I thought, why not, put them down. Just for your amusement, since many students are here, I got so many queries after this article, you see, from lots of students, you see, from outside. But from India, there were rare questions, if there was any. So then I asked, you see, Professor Yashpal or somebody, how come, this article I have written and, I'm getting so many queries, and then from within India, it is very simple, you see, Pankaj. The best of the minds, you see, are in Kota, coaching classes, trying to get admitted in IITs, and once they go to IITs, sorry, they are very busy, to say the least. And the other lot is searching for job, you see, so they don't have to, they don't have time to read your articles, wherever they are. Anyway, but those discussions usually resulted, there is an Indian edition also of this book. But the point is, this is the LIGO and the, the gravitational waves and so on. This is a quote from the, a lecture by Kip Thorne that he gave in Bangalore, I think 3 years or 4 years ago. So he was describing orbits, you see, around black holes. And then he asked this question, because you see, okay, I'm just about to close. Then he asked this question. This is available, by the way, on ICTS website and Kip Thorne's lecture. He asked this question that what if the central body is not a black hole? And he didn't stop there. For example, he said a naked singularity. This is his slide. You see, you see, I have to do, you see, all this, Simon, because if I say, it won't carry that much of weight. But वो Kip Thorne कहता है तो, लोग मानेंगे थोड़ा. You see, people will, say, you see. So he asked this thing, and then he said that in that case, you see, wildly different map. Now, in a way, this is reflected in some of our findings also, like this accretion disk profiles that we found, then in this precision, and then, several other things, actually. I don't have time to go into the details. I think it may be a futile attempt, but I'll still, make an attempt. That, I didn't come with any kind of a mission to, just to follow this area or some such thing. I mean, as I said, I used to do, we do cosmology also, and in fact, the LTB models that we, used for collapse, they are very useful for cosmology also. But it's just that, this is turning out to be a very topical area as of now. And nowadays, you can see several papers coming out and so on and so forth. Right now, what we are doing is comparing, you see, the various predictions by black hole models, the singularity models, by various groups also are working on this issues. So the question is really coming to the observational frontiers. Quantum gravity wise, it would be very interesting. We have a series of papers on high energy collisions of particles near black holes and singularities. So you see, near singularities, very high energy collisions occur. If so, then what are the observational consequences? I know, you see, only little of particle physics and some other things. But then we discuss with colleagues. And we have very interesting discussions. And we do have very exciting phenomena like GRBs, you see, which are again, not so well explained really, despite a lot of effort and so on. So people have tried out this kind of models and so on. Summary is that the profound, you see, work on focusing by Professor Raychaudhuri and the profound work of, you see, I think for the sake of completeness, I must write here, you see, just as I wrote. And not the list, Robert Garrow in USA. So they contributed in a very big way to the analysis of the causal structure, differential geometric analysis. It requires a lot of patience, but it is very rewarding if you go into that. So I guess that's the story. And once again, I thank the organizers and for this opportunity to be with you. Thank you.
We have the floor open for a few questions. Shyam.
Hi. I have a couple of questions, somewhat technical nature. First question is, if the central body of this thing is naked singularity, I mean, I'm not familiar with some details, so you can explain that. Why can't the orbits be much closer than what they are?
In fact, you are right. In the accretion model that we took, the stable circular orbits go very, very close to the singularity. And that is, in fact, one of the key reasons why the accretion profile is, you see.
But won't it then emit more energy, much more energy?
Yeah, it will.
And what are the examples of those? I mean, observationally, I don't know, I'm asking.
No, you're right. So you see, what we have given is a theoretical model of a black hole versus singularity. Now, you see, what some people like Bani Brata Mukhopadhyay tell me is there are some, you see, black hole candidates whose emissions are so high. He, in fact, sent me a list of those objects. I think there is a name for that. Ultra, if anybody remembers, you see this Bani Brata, it's ultra high energy sources, black hole sources. I'll tell the later.
Ultra luminous.
Ultra luminous objects. So yeah, that's right. So, but I haven't done any work on that. But I think people, in fact, say, why not use this?
Sure.
There is another GRB, you see, which is so powerful. So I was discussing with Poonam Chandra, who is a radio astronomer, NCRA. So she, I mean, for the heck of it, let us use these models. Because black holes, it is impossible to explain this. Can we try? So I said, chalo.
Do we know the metric around these objects?
Yeah.
Take negative mass partials.
Yeah.
That's good enough.
Oh, yes. In fact, you see, I didn't have time to write the technical equations, but it is a metric obtained by, you see, myself, Malafarina, and Narayan. So it is known as JMN metric. I'll send you the paper. But yes, we have a very definite metric to work out the stable. Sub legal hai.
But you can just take negative mass partial solution. That's good enough, no?
Legally, whatever is legal procedures followed in general relativity. So, no problem with all that. Sorry.
I have a second question. Second question is related to so you have two situations. In the space-time, either there are naked singularities or there aren't. If there are naked singularities, your global causal structure is very different. So the usual singularity theorem will not go through because you don't have this condition.
No. Sorry, you complete, then I'll tell.
They will not go through in the sense that you don't have the condition which says that conjugate points cannot exist because you no longer have global hyperbolicity or stable causality. in which case I cannot apply the theorem, which is fine, nothing wrong with that. So there are two situations. Either there is already naked singularity, in which case singularity exists anyway, or if the naked singularity is not there, I will have good causal structure, and then Raychaudhuri plus this together will imply singularity theorem under the condition the trap surface forms or don't, those special conditions. Now my question is there analogous condition to say when can naked singularities form? For example, black hole singularity, when we say trap surfaces should be formed or something, only then the singularity theorem applies. So is there something which says when naked singularity?
So I like to clarify. The singularity being visible or not visible has nothing to do with singularity theorems in the first place. Why? Why? Because singularity theorems just use the focusing, which is, yeah. So that is also absolutely fine. Singularities are visible or not has nothing to do. It has, the singularity being visible has to do with event horizons happening or otherwise.
I understand.
So let me finish. So what I mean to say is singularity theorems do not predict the nature of the singularity, they only predict the existence. Now whether they will be covered or not covered, तो उसके लिए ये hypothesis लाके रखा. It's a completely separate requirement and it is a bad need. No. If you were to do, the entire of your black hole edifice, तो अगर censorship नहीं है तो भाई पहले black hole बनेगा, singularity बनेगी, that you will have to examine. And the other very important point I must clarify is, at the very least, let us forget about the naked singularities. You can take all this work as implying some constraints on how you can prove cosmic censorship hypothesis, because you see, you will have to exclude all these things somehow. तुम्हारा आपका, your cosmic censorship statement will have to be, because so far we don't have a concrete statement other than a, feeling. Sorry to say this, but you can verify in the literature. So how to formulate the censorship, which is so important. So all these examples will help you, all this work in gravitational collapse will help you, formulate and properly prove. So I am really trying hard that I am objective.
No, I am not opposed to naked singularities. You are misunderstanding my question.
No, but so you see singularity theorems I clarified. Now what was your second question?
There I still have the question.
Oh, sure.
Because singularity theorem, as you pointed out yourself, there is a conflict between two results. Raychaudhuri equation under some conditions says conjugate points must exist, and causal structure good behavior says conjugate points cannot exist. That assumes that so unless both conditions are there, I don't get the incompleteness.
You don't get?
Incompleteness of geodesy.
Yeah.
Right. Now, once you have naked singularities, you don't have the causal structure as expected. Global hyperbolicity or stable causality is still there?
Yeah. See, the nostrum spacetime also has a naked singularity. You see partial Cauchy surfaces, you have horizons, all causal structure will be there. The only thing is its nature will change, for example, with Schwarzschild spacetime. All causal structure will be there. There's no problem with all that.
I need to understand that. I don't understand.
I'll explain to you, but you see,
I understand.
That's why I gave a very simple.
If the same, then it's okay. Then
No, everything is okay. Everything is okay. See, otherwise, I'll not waste my time.
No, otherwise also it is okay. I'm not objecting, but it will simply get two categories of space-time. One which are causally well behaved in the conventional sense, and ones which are not. But that doesn't matter. I'm not objecting to it.
See,
but how do I distinguish the two cases under physical conditions?
Shyam, I will put it this way: that you see, the causal structure changes.
Yeah, that of course it has to
change. When I work out a homogeneous collapse, causal structure is of one type. When I put in a inhomogeneity, the causal structure is of different type. And I showed in the diagram that when I have a completely homogeneous collapse, then event horizon is forming earlier. When I have inhomogeneous collapse, it forms later. In some cases, it doesn't even come. But causal structure doesn't care, it is not all about event horizons only. Causal structure has to do many things with partial Cauchy surface, global hyperbolicity, other conditions. So singularity theorems are fine. They are showing the existence. Now after the existence, what are they? So then come the collapse models and details of the...
Hello. So the Penrose-Hawking singularity theorems assume certain energy conditions. But we know that if we treat the matter quantum mechanically, most of the known energy conditions are violated. So what is the status of the singularity theorem when the matter is quantum mechanically treated?
They are roughly fine. When I say roughly fine, people investigated this, that suppose you have a trajectory. Now this RAB, yeah, I wrote it all right. I just verified in haste, I did some mess up. The equations are okay. So this RAB, VAVB greater than or equal to 0 is kind of energy condition. Now suppose you have a trajectory, you see, going in time. So if along some patches, if the energy condition is violated, say for example, then people have, in the original Penrose theorem, it was assumed to be correct throughout. But in the revised, theorems versions, people say that if integrated, energy contribution is positive, still the singularities occur. So it allows for violations of energy conditions. In fact, just to complete, we just put up a paper, you see, some time ago, a few days ago, this phantom fields and, where the equation of state is, you see, very sort of parameter is very negative and so on. So in those models also, in fact, many singularities develop. They don't avoid. So violation of energy condition by itself doesn't negate the singularities.
Right, but the average conditions that you're talking about, the integrated conditions, even those are violated in certain scenarios, right? For the quantum mechanical matter.
Yeah.
So, what are the alternatives do we have even there? Even the NAC is not...
He's saying even in phantom, classically it will be violated.
No, not classically.
That's what I'm saying. I think he's saying that even classically it's violated, those conditions will apply to the quantum systems as well.
Okay.
I believe that's what you're saying.
Yeah, no, you are right. You are right. See, the singularity theorems are all classical people. You see, they don't care. I mean, from where you bring in this violation, quantum or, whatever, they say, oh, it is violated. ठीक है. If, on average it is positive, then I am okay. So those kind of results are there. I am telling you the facts.
Thank you. Are there any questions from the students? Any questions? Or we can ask you. Okay, Pato.
No, this is actually on behalf of the students, Pankaj. You gave an excellent talk, like always, but there are lots of technical things which were hidden. But I want to go back to the very beginning when you talked about regions of space-time where curvatures diverge, densities diverge, everything diverges. So we are talking about curvatures diverging at some region of space-time, which means the geometry breaks down. There is no smooth geometry there anymore. When you say density diverging, you're talking about infinite density, which is physically meaningless. So we have regions of space-time, let's say out there, where it's neither mathematically meaningful nor physically meaningful. Now, I think this would be painful in some sense for any physicist or mathematician to think of that region of space as being in God or in hell or somewhere, right? Because it's certainly not part of physical space-time where you and I can exist. So when you talk about singularities, I think you always have in mind a quantum takeover at some point.
Absolutely.
Right?
Absolutely.
So it's not that things diverge, but that the description breaks down.
In fact, in my Scientific American article, I called them quantum stars.
Okay.
Again, it's not picking up.
I haven't read it, but I guess that's, then we
I mean, people are stuck with, you see, in fact, I tried to, introduce this terminology that, and in fact, this in our PRL paper, we showed exactly the emergence of, due to loop quantum gravity effects, the emergence of very high negative pressures. So the ball will be, dispersed basically, and there is no singularity. So that's why we called it quantum resolution. So in fact, so I'm not at all for singularities. But then you see, we have to, do something new. Like this loop quantum gravity simple model, but again it has to be worked out in more detail. But positively, but the key thing is, you see, the singularity being visible vis-a-vis not being visible itself is physically a very big change. Because when they are visible, then this ultra strong gravity regions, even if it's a resolved fuzzball, quantum resolved fuzzball, and it could be some object where entire quantum gravity effect is happening, who knows. But then the point is that fuzzball is, you see, in principle visible. Causal structure, classical causal structure, which would be valid a little far away. So that becomes visible in principle, whereas in black hole case, even that would be hidden, even if the singularity is resolved.
In a way, you're saying that if naked singularities did exist, it'd be a great place to look for quantum gravity effects.
That's, I think, what I'm trying to emphasize. Because, you see, we have this quantum gravity theories, we keep trying. You see, in quantum gravity in curved space-time, then loop quantum gravity, string theory, so on and so forth. I don't think we seem to have, really a good handle. So you see, that's what I was discussing with some of our friends in the morning, that, before we can really formulate a, good quantum theory of gravity, we need to have some observational, you see, and this is the possibility. And it's a valid possibility that way. So that's the whole philosophy. Otherwise, singularities, you see, let us not worry, I mean. Yeah.
Thank you, Pathu. Are there any other questions? Yeah, Pratik. Your microphone.
Yeah, hello, sir. So I was interested that you said that some efforts are being planned to study emissions, these ultraluminous objects, using the naked singularity metric. So I was just curious whether these studies are being planned to study shocked emissions from accretion disks around naked singularities, and does that involve jet formations?
In fact, we have a preliminary model still unpublished, even for jet.
Yes.
Accretion we have studied. Mm-hmm. I mean, the accretion models we have studied. In fact, in one of the papers with Saurabh, and it's there on archives. Mm-hmm. So there we have used a fairly, more realistic model of accretion disk, introducing some viscosity and some more physical effects. We are still nowhere close to Harvard and those who have very complicated programs to deal with accretion disk. But this is somewhat more realistic model compared to what I showed, where it was a more simpler accretion disk. It was a spherical disk, but then in another paper, we took the disk with, that was published in JCAP. But now this paper, we have more realistic accretion disk.
And this is MHD?
Huh?
This is GR MHD, so it involves the magnetic hydrodynamics in...
Yeah.
Just a moment.
Yeah, so he's saying it's radiatively inefficient, so that's why.
This is not a GRMSD, this is the RIAP model.
What model?
Radiatively inefficient accretion flow.
So it's not MHD in...
No, it's taking GR effect in terms of thermal emission.
Oh, so it's not due to magnetic field. That's what you're saying. It's not non-thermal radiation. Yes. That's what you're saying. Okay. Thanks.
Any other questions? Okay, if there are no more questions, I have one. You talked about black hole singularities. Do you have any
black
black
hole.
hole singularities? I mean, what about the cosmological one? There is geodesic incompleteness there as well.
You're right. In fact, Big Bang singularity in principle is a visible singularity. It is a naked singularity. But now that you asked this question, a very interesting point, in fact, emerges. The chalk stick here.
Because it's strange, to my understanding, unless there is a singularity, you won't have geodesic incompleteness in the context of Big Bang.
Yeah. You're right.
Okay.
You're right. You're right. Yeah. See, the Big Bang is something like this. You have t equal to 0, the present epoch. And then you go back into the past. And then you have a singularity at some t equal to Ts. And that's a simultaneous singularity. But here the entire matter distribution is homogeneous because we are in FRW. So instead, if you took the Tolman paper of 1934, you see, and take here, for example, density variation, that is, you see, for example, the matter and voids kind of a thing. Then the structure of the singularity in the past is very curious. You can exactly evolve using the whole thing using the Tolman metric. 1934, I think that is the date. So then this singularity itself can have, you see, some null pieces and time-like pieces and so on and so forth. So I was very curious if this could be used somehow. Inflation, this mixing and all these issues are there. That is all basically because of the, completely simultaneous singularity. But if you have a mixing right in the early universe, and this is very easy to work out actually. I am throwing, a problem to all, the young guys. I mean, it's a Tolman metric is not too bad actually. I mean, if you give me time, you see, half an hour, I'll write down all equations and, explain to you. But maybe some other time. But the point is that it's a very curious nature of initial singularity, and then this inflation thing, some issues may be, helped.
Okay.
That is my suspicion. But yeah, was that your question? Sorry.
No, I mean, my question was related to the other point.
Yeah.
I mean,
So these are all incomplete geodesics in the past.
Right. Okay. And it's naked singularity.
I mean, yeah, in principle it is visible.
Yeah, I understand.
In practice, we will have all sorts of opacity and this and that. But we are, yeah, it is naked singularity.
Okay.
It's a cosmological visible singularity. Sure.
Thank you. Let's thank Professor Joshi again for an interesting lecture.